Okay, so I wish to thank you very much for this invitation, and it's a great pleasure for me to be here. So I'm going to start straight with this problem I'd like to introduce, which I would say that arises in a natural way from the basic case, which is essentially equivalent to the prime number theorem. So I'm sure all of you know the von Mangold function, which is defined for the positive integers as log p if n is a power of a prime p and 0 otherwise. And it is an elementary fact, a classical result, to prove that if we take the least common multiple of the first n integers, the logarithm of this can be written as the partial sum, essentially, of the von Mangold function. And this is the classical Chebyshev function, psi of n. So an equivalent formulation of the prime number theorem says that psi of n is asymptotic to n. So from this, we can say that the logarithm of the least common multiple of the first n integers is asymptotic to n. So we want to try to generalize this function. So this can be done, for instance, by studying the behavior of psi of a, where we consider not just the first n integers, but we take a in a random set of 1n. Okay, so for a random set, and then we let capital N goes to infinity. So at this point, we need to fix our probabilistic model. So we need to say what we mean by saying that we take a random set. And there are more than one possibilities for this. So the first, for the first model, which is probably, at least in my head, it is probably the most natural one, consists into choosing A independently at random in the set 1n with the probability some delta, which is typically a function of n. And it is a result by Cilleruelo and collaborators that when delta is less than 1 and delta n goes to infinity, then we have an almost sure convergent result of psi of A. In particular, psi of A is going to be asymptotic to n times this quantity here, asymptotically almost surely when capital N goes to infinity. Yes?
You mean every element is chosen independently?
Yeah, every subset A. Every subset A. And note that, yeah, we can build again the basic Chebyshev case by letting delta equals to 1, since the limit as delta goes to 1 of the above quantity is 1. So this is the limit case. Okay, so another possible probabilistic model we can consider is this one. So this time we choose A independently at random among the subset of a fixed order. So we fix k, a positive integer, which is a function of n, and we choose A amongst the subsets of order k of 1n. And again, we have a result by Cilleruelo saying that if k is less than n, which of course makes sense, and as k goes to infinity, then psi of A is equal to this quantity here, again asymptotically almost surely as capital N goes to infinity. So we in this case we have an explicit error term. Also in the previous case it is possible to make the error term explicit, but it's not relevant at this stage. And again, the case, the limit case k equals n corresponds to the Chebyshev function situation. So since the limit as k over n tends to 1 of the main term in the above is 1. And if we want to compare the two models, the heuristics suggest that the two models are similar, are comparable when delta is equal to k over n. Okay, so we can make a comparison between the two. All right.
Can I have a question?
Sure.
This error term is the same as in classical prime number theorem, right?
Yeah.
It comes from prime number theorem.
Yeah, exactly. This-
a Riemann hypothesis is with probability 1 sure, correct?
Mhm.
So one can expect a much better error term.
Yeah, yeah, exactly. This uses like the classical error term from the prime number theorem.
Yeah,
The,
but even
by assuming
think,
by assuming the Riemann
this-
hypothesis, yeah.
this should be 1 over square root of k.
By assuming the Riemann hypothesis.
Yeah.
Yeah.
But without Riemann hypothesis, but in this random model.
Without Riemann hypothesis,
Yeah. Because
um,
Riemann hypothesis is almost sure correct.
okay, yeah, okay, I get.
So in a random model, there should be the same as the error term, assuming Riemann hypothesis. So much better than this.
Yeah, so in Cilleruelo result, they don't take into account Riemann hypothesis or something, but I'm pretty confident that it is possible to improve these error terms. Yes, it should be possible. And actually, in the next generalization that we see, I'm going to assume the Riemann hypothesis in some case, but maybe just since here is just an almost sure convergence result, maybe even without assuming it is feasible. Okay, so this is the first generalization to the basic Chebyshev function, but actually, in this case, we are interested to another possible generalization consisting of taking a polynomial. So let's consider the basic case, which is polynomial with coefficients over z, and we consider the least common multiples of the first n values of the polynomial to the first n integers and taking the logarithm. So we are interested to an asymptotic behavior of this function psi f of n. So for sure, again, the prime number theorem is equivalent to the asymptotic psi f of n asymptotic to n, and this is the case corresponding to the polynomial f of x equals to x. So next step is asking what happens when we consider linear polynomials more generally. And for polynomials with integer coefficients, this time we call the prime number theorem for arithmetic progressions, so the Dirichlet theorem, which leads to an asymptotic for this psi f of n for linear polynomials f of x of the form xk plus h, where h and k are coprime. This is due to Bateman-Kalbe-Starger, which proved that the growth is linear in particular. So it is n times this constant, where phi of k is the Euler function counting the numbers less or equal, the integers less or equal than k coprime with k, and then the sum is over the integers up to n coprime with up to k, coprime with k. Always as capital N goes to infinity. So with respect to the previous generalization, this corresponds to the set AFN, okay, where AFN is the set of values of polynomials f of k, where f of k is less or equal than capital N. They are not identical, these two functions, but for sure this is the right correspondence. Okay. So what we want to do is first we want to generalize this result of linear polynomials by considering polynomials with coefficients more generally over a number field, integral over a fixed number field, and then of course we want to understand what happens when we increase the degree of the polynomial. So let's start with this linear polynomials over a number fields. So I hope to not be tedious with this part, because I want to recall some definitions of Ray class groups and so on. So I hope to not be too tedious, but I also need this to fix the notations. Okay, so let's fix from now on this number field k over q of degree d, and I recall that the modulus on k is just a function from the prime ideals of k into z, so it is non-negative for all primes p. It is 0 most of the time, so for all but finitely many p. It is also defined for the prime set infinity, and in particular it is 0, 1 for the real primes, and we don't have to worry about complex primes because it is 0. So we can write it with some abuse of notation, M as the product of the primes to the MP. Okay, this is very handy to have in mind. Okay, that's the modulus, a modulus on a number field. This subset, the subset Km1, is defined to be the set of non-zero elements of K, so that the order at P of A minus 1 is greater or equal than MP, so the order at P is just the highest power of P dividing the ideal generated by A minus 1 in OK. So this condition simply means that A is congruent to 1 modulo P to the MP. Okay, it is equivalent to that. That's the fact for the, That's for the finite primes dividing the modulus M, and we also have a condition for the real primes. So the Ray class group modulo M is defined to be ISM, the free abelian group generated by the prime ideals which are not in the modulus M modulo this Km1. Actually, this is another abuse of notation because Km1 can be embedded into ISM since each element in Km1 generates an ideal which is a coprime with each prime ideal in the modulus M. Okay, so this is the Ray class group. So a few examples to have in mind. So if we if you consider the modulus, which is 0 for all primes P, then we take we get the classical ideal class group. Okay, so Cm is the ideal class group. Ideal class group. Then I have other few examples. Actually, just one, which is always good to have some in mind. So, for instance, let's take this modulus on over Q. So let's take our favorite number field. So let's take M, for instance, this one, just a random one. Okay, so let's see what the set Qm1 is in this case. So Qm1 consists. Okay, so let's add also the prime at infinity. So the only prime at infinity of Q. So in this way, I can say that Qm1 consists of the positive rational numbers such that, so maybe I can move to another blackboard if you, sure. Which one? This one? Okay.
We use all of them.
Okay, so maybe it's easier for you to. Okay, so Qm1 is the set of all positive rational numbers. So let's see what is the condition at 2. The condition at 2 says that the order. So let me write. Okay, so A in Q positive, so that the order at 2 of A minus 1 is greater or equal than 3, which is the exponent, and the same, the order at 17 of A minus 1 is greater or equal than, the exponent was 2, and the order at 19 of A minus 1, greater or equal than 1. Okay, so for instance, the condition at 2 says that A is a quotient of 2 odd integers, okay, and also that, so conditions at 2, the other one can be expressed similarly. So A can be written as B over C, where C is non-zero and B and C are not divided by 2, so they are odd numbers. And also and also that the image of B, I'm going to write it this way because I want the image of this in Z modulo 2 to the 3Z, so 8Z units, is 1. That's what means exactly, and the other conditions are similar. Okay, so in this case, this follows from a more general exact sequence, which holds in general for the Ray class group. It follows that in this case, the Ray class group is isomorphic to, so if I call the modulus M times infinity, so M is the finite part, the Ray class group is isomorphic to Z modulus MZ units. Okay? And what happens when I consider just this one without the prime at infinity? So it can be shown, it's not hard to show that in this case Cm is isomorphic to Z. The same, but I had to go modulo plus minus 1. Okay, that's a few basic examples for the Ray class group. Okay, I should down again. All right, so we got the definition of this. Now, let's take an ideal, which is not divided by any prime ideal, dividing the modulus M. And again, in this case, we can consider the Chebyshev function associated to the modulus and to the ideals, to the ideal C, theta x Cm, which is the sum over the prime ideals of norm less or equal than x, which are in the same Ray class group, modulo the modulus M, and it is a classical result that it is equal to x over hm, which is the Ray class number, the order of the Ray class group, which is a finite abelian group, plus an error term, which can be explicit as well.
S is missing on the left.
There is missing.
Exponent S is missing. Norm of P to power S, probably.
Norm of P to the S. No, I think this is just corresponding to like the classical theta function.
It's not the
Yeah, but what is S then? On the left, there's no S.
which equation? Oh, you mean the second equation?
The second
Ah, yeah,
equation.
okay, right.
This one.
Yeah.
Yes. There should be S.
Ah, yeah, it's not P to the S. Yeah, this one. I thought the first one. Yeah, I forgot this. Yeah, this is equivalent. This can be expressed equivalently in terms of Dirichlet density. That's why. It means that the set of prime ideals congruent to a given one in the Ray class group of 1 over the norm of P to the S is asymptotic of 1 over HM logarithm of 1 over S minus 1 as S approaches 1 from real values greater than 1. That's what it means. Yes?
Excuse me, but to make an analogon of the Chebyshev function, you would have to include the powers of prime ideals, right?
I have to include, for the...
Not just the primes.
It's a different Chebyshev function.
for the other Chebyshev function,
Well,
the psi one.
this is the theta, right? And
The psi one, yeah.
would include.
Yeah, I'm just going to use the theta function in this case. So yeah, but we also need the generalization of the von Mangold function in this case, yes. Yeah, but I definitely miss an S there. Okay. Now, okay, I just want to state some of the explicit error terms for this theta function. So this is another, we could say, classical result from Lagarius and Dot-Glitzo, and this one is conditional to the generalized Riemann hypothesis for the Dedekind zeta function associated to the field K. It says that for any ideal coprime with the modulus M, then theta is asymptotic to x over hm, and the error term is of size square root of x log x square, so the constant depending on k and n can be made more explicit actually, but I don't need in this case, so I just write in this way as x goes to infinity. This is a conditional result. We also have an unconditional version of this, always due to Lagarius and Totlisko, saying that so we know that the Dedekind zeta function has at most one Siegel 0, beta 0. If it exists, it is real and simple, and the real part it is in this range. And yeah, the error term in this case takes this form, and the term x to the beta 0 exists if and only if the Siegel 0 exists. Okay, this also to have an unconditional version of this. Now, okay, so now let's go back to our problem. So I recall that we are interested to have an asymptotic formula for the least common multiple of values of polynomials with coefficient over the ring of algebraic integers of k. So first of all, we need to understand what we mean by least common multiple of elements in OK, right? So lambda 1 and lambda s are integral over k, so we can consider the ideal, the principal ideal they generate lambda I OK, which since we are in a Dedekind domain, we can write the ideal as a product of powers of prime ideals. We have the unique factorization, where the power beta pi is 0 for all but finitely many primes p. And by least common multiple of lambda 1 of these S elements in OK, we mean the least common multiples of the ideals they generate, okay? And the least common multiple of the ideals is defined as the intersection of the prime ideals dividing the ideal the elements generate to the maximum of the powers, which by, for instance, by the Chinese remainder theorem, this was also the product of over all the prime ideals to the maximum of the power. Okay, so that's what we mean. Now let me define this quantity, which also allows us to have a result which is a bit more general rather than just taking values of polynomials. So let's fix a modulus of k and an ideal coprime with each prime ideal dividing the modulus m. Now S of m is the set of ideals, of integral ideals of k of norm less or equal than m in the same Ray class group modulo the modulus m. Okay, so the reason why I'm using capital M and non-capital N is going to be hopefully clear later, because I need capital N for another quantity. Okay, so the first result is an asymptotic for the logarithm of the least common multiple of Sm, or more precisely, so this makes sense, right? Because S of m is a set of ideals. The least common multiple we saw it is an ideal, so we can take the norm from k over q and then the logarithm. So this quantity makes sense. And assuming the generalized Riemann hypothesis for the Dedekind zeta function, we can use Dirichlet theorem over number fields, the explicit version, to achieve that this logarithm is asymptotic, is linear again. It is asymptotic in particular to m times this quantity, 1 over the Ray class number, and the sum is over the representatives of each class in Cm, 1 over the norm of C. So by norm of C, as I wrote down, is by definition the smallest norm of an integral ideal in the Ray class of in the Ray class group of C. It can be proved that each Ray class has an integral ideal which can be taken as a representative. And in this case, we take the one of smallest norm, plus an error term which is of the size of this size. So in this case, we clearly using the conditional result for the theta function. And if we don't want to assume the generalized Riemann hypothesis, so there is a possible Siegel 0 for the Dedekind zeta function, and then we achieve the analogous result, but with another the error term corresponding to this situation as m goes to infinity. So at this point, it is probably not completely clear how this has to do with polynomials, right? Because we want to find an asymptotic for the least common multiple of values of polynomials to integral elements. But this situation is related to that because if we consider principal modulus, so let's take a modulus generated by an element in OK, then take alpha coprime with the ni, I mean that the two ideals they generate are coprime. Then this time define Sm, which is, I use the same notation, but it is a bit different because this time Sm is the set of principal ideals in OK of bounded norm, which are in the same ray class of our fixed alpha. And it is not hard to show that Sm is equal to the set of this evaluation of these polynomials f eta of lambda, where lambda is an integral element of bounded norm by a constant times m, and eta is a unit in OK, is in the group of units of OK, plus a negligible error term with respect to the previous error term we saw. And the f of eta is a linear polynomial, so now that's what we want, right? We want the case of linear polynomials of the form eta alpha plus ni x, where eta is a unit. Except that this time we have a family of linear polynomials because we need to take into account the units of OK. And by using the previous result, we have that the logarithm of the norm of the least common multiple of these values of polynomials to integral elements of bounded norm as a linear growth as before. Of course, the error term here I just wrote down a little o of m, but it can be more explicit. So let me just explain very roughly the reason behind it. So the reason why Sm can be expressed in this way, but this has to do with the fact that so if we have that beta is in the same class of alpha in Cm, then it can be proved that this follows from a more general fact. Then we know that there exist A and B in OK, not all zero, not zero, so that A is congruent to B and congruent to 1 in modulo M, and in our case it was a principal one, so modulo ni, and beta times B is equal to alpha times A. Okay, so that's the reason, the main reason behind it. All right. So here we can skip this. Okay, so now next step, we just saw the case of linear polynomials. Now we want to go into quadratic polynomials. So this is again the situation for polynomials with coefficients over z. This is a result again due to Cilleruelo, saying that, so starting from quadratic polynomials, the growth is no longer linear. So it is n log n particular, and for irreducible quadratic polynomials of this form, we have that the logarithm of the least common multiple of f1, fn is n log n plus this constant here, bfn plus little o of n. So this constant involves many quantities. In particular, gamma is the Euler constant. This is the discriminant, E over B the Kronecker symbol, the generalization to the Legendre symbol, and the SF p to the k is the number of solution of f modulo p to the k. I'm going to use this notation later as well. And this SF p to the k can be computed by using elementary manipulation of Ainsl's lemma. So for instance, one can prove that SF p to the k is 1 plus the Legendre symbol dp whenever p does not divide to AD, where A is the leading coefficient. Okay, and also the other cases can be computed by using Ainsley lemma. So it is also possible to generalize it for polynomials with coefficients over OK, so the result is pretty much the same, and the constant BF is much more complicated. But I wouldn't like to focus that much in this situation to the quadratic case, because I would like to start considering higher degrees. Okay, so let's see what happens when we increase the degree of the polynomial. So polynomials with coefficients over z, what is known? Okay, so for f with non-negative integer coefficient, it is known lower bound. We know that the logarithm of the least common multiples is greater than n. However, for the case of irreducible polynomials, or degree greater or equal than 3, Cilleruelo conjectured that the growth is more than linear, as I mentioned before. And that's exactly the statement of Cilleruelo conjecture. So if f is in a reducible polynomials with degree at least 2, then the logarithm of the least common multiple is asymptotic to the degree of f minus 1 n log n, as n goes to infinity. So we saw before that the Cilleruelo conjecture has been proved by Cilleruelo himself for quadratic polynomials, but no other case is known up to date for degree greater or equal than 3. What is known is lower bound. The logarithm is less or equal than the degree of f minus 1 n log n, and also, that was an upper bound, and also it is known a lower bound. More recently, Rudnick and Zehavi proved that the conjecture holds for almost all f in a suitable sense, so they have an average result. And in the following, I'm also going to state an average result, but the difference is that first we consider polynomials, more generally polynomials with coefficients over the ring of algebraic integers, and we take the polynomials in a very specific family, so there are intervals which are not included in their result, and of course we can reconstruct their result if we let the polynomials to have coefficients over z. All right, so what I have to do now is introduce the family of polynomials I want to consider to study this problem. The reason why I want to use this family is because it has some special average properties which are going to be useful to achieve results in order to apply it to prove an average version of a Cilleruelo conjecture. So our number field k over q is fixed of degree d, and take small n greater or equal than 2, which is going to be the degree of the polynomials, which is going to be fixed, and the capital N greater than 0, which is going to be the so-called high of the polynomials. So we consider the set Pn and k of polynomials of this form. So they are degree n, monic, and the coefficients are over OK. We can write the coefficients in an integral basis of OK over z, so these other coefficients a, I, k are integers, and we assume that their absolute value is less or equal than capital N. So that's the so-called high of the polynomial, which we assume to be less or equal than capital N, and then we let capital N goes to infinity. And our probabilistic model is the following. So we view this a, I, k as independent, identically uniformly distributed random variables taking values in minus capital N, capital N. So let's think about if we take f with coefficient over z, we just consider polynomials so that the coefficients are of absolute, the maximum of the absolute value of the coefficient is less or equal than capital N. This is just the generalization for number fields. Then we consider the subset of Pnn 0k to be the set of so-called Sn polynomials, so polynomials of this form, so that the Galois group, I can just is it? The Galois group of the splitting field of the polynomial over Q is the full symmetric group. So we have the situation. Sorry for that. It's long. The situation is this. So we have the splitting field over K, and this is the Galois group, which we assume to be the full symmetric group, Sn. Okay, so this is our family of polynomials, which is not, it's kind of natural to consider it because almost all polynomials are Sn polynomials if we order them by their height, okay? So in particular, we have this result about counting Sn polynomials over K. So this set here, Pn(k) minus Pn(0)k is, of course, the set of non-Sn polynomials. We can prove that it is less than this quantity here. So the first situation is just the case of quadratic polynomial, which is by its own, but later we are going to just consider degree greater or equal than 3. And the reason why we need to separate it is because at some point we need to count, to take into account for this quantity here the number of reducible polynomials, which corresponds to polynomial having Galois group intransitive subgroup of Sn. Okay, and for the case of degree 2, we have to basically put an extra epsilon on the exponent. That's why there is this log n. Extra log n for the case of degree 2. So the second part, I included it just to include like all possible values of d, which is the degree of the number field, and the degree of the polynomials. So this can be proved by using large sieve over number fields. So we basically identify the polynomial f to the lattice vector formed by its coefficient, and then we use large sieve. The third one is probably the most interesting one, which can be viewed as a generalization of the so-called van der Waerden conjecture, which is the same problem but just for coefficients over z. Just for coefficients over z, which has recently in 2021 been proved by Bhargava, saying that in this case the number of non-Sn polynomials is less than n to the dn minus 1. Okay, so yeah, we need to distinguish between some values of n and d. So the first one is the case over Q, the one I already mentioned, proved by Bhargava, and here we have to distinguish between some values. So the reason why we have to do that is roughly that at some point in a step in the proof, we need to use an asymptotic for the number of field extension having bounded discriminant. And in that case, of course, we try to use the best result known up to date. So that's why we need to distinguish between cases of n and d. However, this is counting Sn polynomials, which is the first step. Now, take a polynomial, an S polynomial of I less or equal than capital N, and take a prime ideal. The splitting type of f modulo p is this vector, R1, Rn. It means that f modulo p splits into R1 linear factor, R2 quadratic factor, and so on. And we just consider square-free factorization. For the primes not dividing the discriminant, so this dkfk is the ideal discriminant of the extension. So for the unramified primes, this R corresponds to the cycle structure of the Frobenius element. This is classical Frobenius theorem. Okay, and we view the Frobenius as a permutation of the roots of the polynomial. Okay, so this I Ri are a partition of n, and the order of a conjugacy class in Sn is known, it is n factorial times this delta R, which is this quantity here. Okay, so recall that the symmetric group has a special property that the conjugacy classes are fully defined by the cycle structure of the elements. This is not true for any transitive subgroup of Sn, because maybe there are some conjugate classes which splits into different one in a subgroup. But for Sn, the cycle structure fully determines a conjugacy class. That's why we can define in this way a Chebotarev density theorem function, which is what we want. So pi fr of x is the sum of the prime ideals of norm up to x, so that f is split in type R modulo p, which is equivalent to say that the Frobenius at p is in the conjugacy class of element of cycle type R, which we can write it as a sum of random variables, one frp, of course one frp takes value 1 if and only if R is split in type R modulo p and 0 otherwise. Okay, and we view, in our probabilistic model, we view pi and n 0, I forgot the k, as a subset of minus n to the nd, okay, because we identify each polynomial with the vector of each coefficient, and this small n times t correspond to the number of choices we have for each coefficient of f. Okay, and then we denote by Pn the uniform probability measure on this set, En the same, and sigma n square the variance. So we are on our way to achieve a Chebotarev density theorem on average. How can we use it to prove a Cilleruelo conjecture? I'm going to explain. But first, Chebotarev density theorem on average. So in order to include all the possible cases of n and d, we can write the error term for the number of non-Sn polynomials in this way as n to the dn minus xi, where xi is 1/2 minus epsilon. This epsilon was that logarithm for all n and d. If, moreover, n satisfies one of the additional conditions, that was the Van der Waerden conjecture for number fields, then we can take xi equals to 1. And the effective Chebotarev density theorem on average is the following. So when x is quite small compared to capital N, in particular, it has to be smaller than this power of capital N, and this is crucial. This is crucial in order to prove this. Then we have that the average, the mean value of pi fr of x is delta r pi k of x. Pi k of x is the prime ideal function counting prime ideals of norm less or equal than x. And this is the expected term by the classical Chebotarev density theorem. But we also have a second order term of size log x, and CR is an explicit constant. And an error term of order big O of 1, and the implied constant depending on n and k, as x and capital N goes to infinity. Of course, this restriction is going to induce further restriction on our problem. But the reason why we need to be in this range of x and n is, roughly speaking, is due to the fact that if we are in this range, that we have enough polynomials in our set which are congruent to a given one modulo prime p. That's the main point. Okay, Cilleruelo conjecture for our family of Sn polynomials. Okay, so I'm gonna denote this our quantity logarithm of the norm of the least common multiple of f of lambda, where lambda is an integral element of bounded norm by psi and m. It depends both on n and m. And the result is the following. So if n and m are quite close to each other, that's what this range says. In particular, n has to be greater than m log m to a small power, and the little o of this other m log m over log m. Then the mean value of the logarithm of the least common multiple is n minus 1 m log n, plus we also have an explicit error term as n and m goes to infinity. So in particular, note that this is exactly what the Cilleruelo conjecture says. Okay, so the degree minus 1 times m log m. We can do the same in order to compute the variance this time. So we also have an estimate for the variance. So in the same range of n and m, we have that the variance is less than this, this term here. So let me just go further a little bit. I want to make the comparison. In particular, we can use the usual the usual inequalities, okay? Since the variance is little o of the square of the mean value as n and m goes to infinity, if we analyze the two results, we can see this that this holds. Then it turns out that in particular the logarithm of the least common multiple is asymptotic to the mean value almost surely, okay? So in particular we can say that for almost all f in Pn and 0k we verified almost surely the Cilleruelo conjecture. So do I still have a few minutes? Okay, I just want maybe to underline the point in the proof in which we use Chebotarev density theorem on average, because I introduce it, so it makes sense to understand where we need it. Okay, so here is a sketch of the proof, but maybe let me just, that's the point in which like Galois theory takes a place. So at this point we need to estimate the following quantity. So the sum over the prime ideals, so I denote by QP the norm of P, that's just a notation. The sum over the prime ideals of norm less or equal than X, which are aramified, so we distinguish between aramified and ramified case. The ramified case is more elementary, I would say, in the proof. But for this case, I applied the Chebotarev density theorem. So the sum of SPF, which is, I changed a bit the notation, but it is the number of solution of F modulo P. This is the number of X, so that F of X is congruent to 0 modulo P. Number of solution of F modulo P. And to do this, we apply Chebotarev density theorem. So in our range, so for X less than this power of capital N, that's why we need to consider those range of capital N and capital M. This is one of the reasons. We have that the mean value of this can be written as the sum over the integral elements, sum over the elements in the Galois group GF, which is just Sn. Okay, so GF is just Sn, so the number of permutations fixing alpha, times the mean value, which I put at the end of the function pi fr of x, and we can use our result to say that this is pi k of x plus big O of log s. I just used the second term. I included the second order term in the error term, and this is because, okay, so this CR for some R is the set of conjugacy classes inside Sn. So that's the part in which we use the Chebotarev density theorem on average, and this final observation allows us, I'm repeating myself, allows us to say that almost surely Cilleruelo conjecture is satisfied for almost all polynomials, and we also have an explicit error term, as I showed before. So I think I'm gonna stop here, and thank you very much.
Thank you so much. Are there any questions? So it seems that everything was clear.
Oh, thanks.
What are your next plans in this subject?
Okay, next plan in this subject. So first, I'd like to consider the case of reducible polynomials, which we can achieve lower bounds and upper bounds in this case, and
Is it simpler to have reducible polynomials?
okay, so I think Chebotarev density theorem is not needed in that case, or at least I mean what I tried so far. We don't need the Chebotarev density theorem, and also there is something which has been studied for the case of polynomials over Z, which is the Chebyshev. I should have some notes about it. Let me just, Chebyshev problems. It's written, otherwise. Chebyshev problem, which is related to it because, okay, so the classical Chebyshev problem consists into finding lower bounds for this function pi plus of n, which is the largest prime factor dividing n. Okay, so the largest prime factor of n, and this is one lower bound. This is greater than n. So in our case, we'd like to study p plus of f of n, where f is a polynomial with coefficients over z. And of course, I would like to generalize it for polynomials over OK. So this is a result by Rudnick. Rudnick proved again that this is greater than n for a positive proportion of the integers. So for positive proportion, of integers n. We can be more precise. At least I think they prove it for at least 1 minus 1 over d integers n, where d is the degree of the polynomials. Okay, so that's this Chebyshev problems like this. The idea is to generalize them to.
The largest prime dividing n is greater than n. What do you mean by?
The largest prime factor of n.
Is greater than n.
Yeah, to the power.
But it's,
To the power.
Of f of n, not of n, right?
That
F of n can be greater than n, so it can have a larger prime factor.
yeah, f of n. F of n. Yes,
But the
forgot.
The fifth line.
Wow, f of n.
Strange.
F of n. Yes. Yeah. I don't remember if I have to put the condition that all the coefficients of f are positive. Maybe I should. Maybe I should. Or put an absolute value somewhere. Something like this. Yeah, that's the next thing I would like to study, for instance.
I wonder about these generalizations to number fields.
Mm-hmm.
They invite a lot of technical problems, for sure, because algebra is more complicated. But somehow I feel that the most important case is rational case. Do you agree with that?
The most important case, well, for sure, yeah, it's the starting point. Yeah. For instance, for the van der Waerden conjecture, so it has been proved for all degrees. But for the case of polynomials with coefficients over z, since we need these bounds for like a field extension of bounded discriminant, for instance, then we have some problems with that because they varies according to the degree of the number fields and the properties of the number fields. So maybe we should have a better understanding of these results in order to improve also this one for the case of number fields. That's what I feel to say. Yeah.
Thank you.
Thank you.
Any other questions? If not, let us thank Ilaria again.
Thanks.